So that's going to relate to this lovely idea of, remember this? Remember acoustic impedance and attenuation and all that good stuff? Something to keep in mind is that the word impedance really means resistance. If you impede somebody, you prevent them from moving forward, you offer some resistance. And acoustic impedance is a property of the medium, and it's the density of that medium times the propagation velocity of that medium. And remember, in order to get a signal to happen, we have to have that acoustic impedance mismatch thing. And we have this big, long equation that told us about what the percentage would be, what percent of the beam would be reflected at different interfaces. So remember, this idea of acoustic impedance not only applies with the body itself, but this also applies to the transducer. Remember, we have the transducer construction, and we talked about the PZT layer, and we have the backing material, or the damping layer, whatever. And then we have that other layer up here. Right, this was the matching layer. What was the whole purpose of the matching layer? Right, it's to lessen the acoustic impedance mismatch between the crystal and soft tissue. So that's also the reason why we use gel. You know, what's the acoustic impedance mismatch between even a matching layer and air is very, very high. So we would have a lot of reflection if we had an air layer in between the matching layer and the skin. So we put that gel in there that also lessens that acoustic impedance mismatch. So not only do we have to be worried about it in relation to reflections in the body, but just even the way the transducer works, we have to have that thing that reduces that acoustic impedance mismatch. Something matched up better. Let's see. Most crystals these days, most transducers these days not only have one matching layer, but they have several. So the one that's touching the transducer face would have an acoustic impedance much closer to the crystal, and then as they move out away from the transducer face, they get closer and closer to the acoustic impedance of tissue. So it even lessens it even more, and lessens that mismatch. But the idea of that whole mismatch thing is the larger the mismatch, the more reflection you get, the smaller the mismatch, the less reflections you get. So something like a fluid-filled cyst doesn't hardly have any acoustic impedance mismatch at all inside of it itself. It's a very homogeneous fluid, so you don't get any reflection, whereas something that's calcific or very dense and has a very high propagation velocity would give a big acoustic impedance mismatch. We get lots of reflection and no transmission. So everybody remember that idea? Let's see. So this is going to form kind of our basis of how this wave interacts with the body. Couple things to keep in mind when we talk about interaction is that the wave is going to, the wave is affected by the medium, so we know that. We've talked about this attenuation idea, we're going to talk about that some more. But remember on the safety side of it, that the wave, this is a form of energy, so it does actually change the medium. That's when we were talking about those acoustic variables, we had the 4 things that are acoustic variables. Those are actually changing in the medium. So we're actually changing the pressure, the density, the temperature, moving these little cells around a little bit. So that's why that bioeffects and safety stuff is so important, is that we are actually interacting with the medium, we are making changes, and we can do damage related to the temperature damage and then mechanical cavitation damage. Okay, so let's go back to how this affects the wave. So we have this whole idea of acoustic impedance and this mismatch, and that leads to our discussion about attenuation. What was attenuation?
Weakening of the beam.
Right, it's a weakening of the beam. So we're actually causing the beam to change in some way. So we had 3 factors. There was absorption, and then we're going to talk about reflection, and then in a minute we'll talk about the third one. So remember there were two things you needed to know about absorption. What were the two things you needed to know? First of all, what is absorption?
Energy to heat.
Yeah. So absorption is conversion of energy to heat, and what were the two things that we needed to know about absorption?
Main form of attenuation.
Yep, it's the dominant form of attenuation. Dominant form of attenuation in soft tissue, and what's the second thing? It increases exponentially with what? Frequency. High frequencies attenuate a lot more than low frequencies, which is why we have problems with depth penetration with high frequency transducers. Okay, so that's all you really need to know about absorption. It's that conversion of energy into heat. It's the dominant form of attenuation. That means that as the wave is interacting with the medium, most of the beam, most of our ultrasound energy that's lost is converted to heat. So we have actually very little that's reflected back to the transducer because a lot of it is lost to absorption. And then we have that refraction thing. Refraction bends the beam off in different directions, so it doesn't even come back to the transducer a lot of the time. But the one thing that's going to weaken or decrease the amount of power that comes back to the transducer out of the body, the main thing that weakens that is absorption. So a lot of the ultrasound energy is converted into heat. Okay, then we have this idea of reflection. Something that I really, really, really want you to get down is that reflection is related to this acoustic impedance mismatch, but not, but refraction is not. So you gotta get the hang of what the acoustic impedance mismatch tells us and what determines refraction. And we'll talk about refraction in a minute. But the amount of reflection, that's what this is. The amount of reflection is this acoustic impedance mismatch. So big mismatch, lots of reflection back. Small mismatch, not much reflection back. And there were two kind of aspects of reflection that we talked about. We talked about the acoustic part, which is this, and then we talked about the geometric part of it, the different types of reflection. And we had things like specular reflection, and we had scattering, and then we had a special form of scattering called Rayleigh scattering. Sometimes you'll see them call scattering backscatter. Same thing. And remember the different ideas with these ones is that with specular reflection, the reflector is large and smooth. With scattering, it's rough. And then Rayleigh scatterers are very small scatterers. So specular reflectors, those big, smooth reflectors, mirror-like reflectors with relation to the wavelength. Scatterers or backscatterers are those rough compared to wavelength scatters. This type of reflection is weaker than the specular. And if you think about that, it should make sense because when we have our drawing, it says here's our medium interface, and we have medium 1 on this side and medium 2 on this side. And if this is large and smooth and flat and I have a beam coming down and hitting it, it's going to bounce a whole bunch of energy back, and we're going to get a very strong reflection off of that. If, however, this medium is bumpy, as that beam comes in, we get scattering in all different directions. Remember in class I talked about throwing a tennis ball? And if I threw a tennis ball at a big, smooth, flat wall, I'm gonna throw it straight at it and it's gonna come back and bump me in the head because I'm really bad at catching, so it hit me. But if I threw the tennis ball at the rough brick wall, every time I threw the tennis ball is gonna bounce in a different direction. So that's why it ends up being weaker. Is that for one, when if you throw the tennis ball at that kind of weird shaped brick wall, when it bounces off the brick wall, it doesn't have as much energy to bounce off of, right? Versus a smooth, flat thing. And then it also kind of goes in all these different directions. So some of it's going to come back to the ultrasound transducer, but some of it's not. Some of it's going to scatter out in different directions. So it's weaker. And then Rayleigh scattering is even weaker. Remember that? I gave the example of a tennis ball at a wall of pebbles. If I could suspend pebbles in the air. If I were to hit the pebble with the tennis ball, I might get a little bit of a reflection of the tennis ball off the pebble, but I'm not going to get much. It's a very, very weak form of reflection. And there's going to be an awful lot of chances there where the tennis ball is going to fly right through the pebbles. So the ultrasound beam is going to fly right through these Rayleigh scatterers and not even be able to reflect off of it. So that's why it's a very, very weak form of reflection. Okay. So that's the idea of reflection. Remember, reflection is always about this acoustic impedance mismatch. That's always what it's about. That in order to determine what kind of reflection we have at all, we have to know what that acoustic impedance mismatch is. Versus refraction. Refraction is the bending of the beam. Right, so the beam is no longer traveling in a straight line. And it has two components that have to be present in order for it to occur. What are the two things that have to be present in order for refraction to occur?
Oblique incidence.
Oblique incidence and different propagation velocities. So this is different than an acoustic impedance mismatch. So there's two components to acoustic impedance, right? There's density and propagation velocity. It is possible that two structures that have a different acoustic impedance or the same acoustic impedance have a different propagation velocity, or opposite, that they have a different propagation velocity but the same impedance, or I don't know, however I said it the first time. Anyway, because there's two different components here, we could have reflection and no refraction, or we can have refraction and no reflection. So you have to really get down that this is reflection, this is refraction. And remember, by all this incidence stuff, this oblique incidence and orthogonal or normal incidence, remember we have our interface. We have medium 1 and medium 2. We always draw the normal line. The normal line is perpendicular to the interface. So if I have normal incidence or orthogonal incidence, I'm coming straight at the medium interface. Normal incidence or orthogonal incidence or 90-degree incidence, all that means that I'm coming straight down at the interface, which means my reflection, assuming that these have different acoustic impedances, if I have an acoustic impedance mismatch, I'm going to get reflection straight out and maybe some transmission straight through. So in this case, no matter what my propagation velocities are, with orthogonal or normal incidence, I'm never going to have refraction because I have to have both, not just one, but both of these have to be there in order for refraction to occur. So in this case, I'm never going to have any refraction. I'm just going to go straight down at the interface, straight out, have a little bit of transmission through, everything's hunky-dory. So at this interface, if I had oblique incidence just means something other than normal. I come down at the interface like this, at an angle, something other than normal, now I have oblique incidence. If I just have an acoustic impedance mismatch, I'll get reflection, and I'll get transmission, and I can measure these angles. Remember, we measured all these angles, and I had the angle of incidence, and I had the angle of reflection, and I had an angle of transmission. And if I just have this acoustic impedance mismatch thing going on, but the propagation velocities are the same, all of these angles would be identical. That the angle of incidence would equal the angle of reflection, and that would equal the angle of transmission. So that's assuming that no refraction has occurred, that my propagation velocities are the same. This would have one propagation velocity, this would have a second one. If they are exactly the same, then I'm not going to have any refraction occurring. If, however, these aren't equal, then I'm going to have some changes going on. And remember, the change that happens with refraction happens to this angle down here. This part always, always, always stays the same. But when refraction occurs, we change this angle. So remember that if we have the propagation speed in medium 1 is greater than the propagation speed in medium 2, then my angle of incidence will be greater than this, and I end up with, or angle of incidence will be greater than the angle of transmission, and I end up with something that looks like that. If, I'll just use this one. If the opposite happens, I bend this way. And what law tells us that?
Snell's.
Snell's law. So remember how to do that, that we kind of said, all right, here's the wave. Remember, this is a wave front. As the wave front comes down, if I'm doing this idea, this side is moving faster than this side as this side hits this medium, so it moves faster, it goes that way. The other way, I'm moving along, and then this end hits this second medium, and it moves faster, so it goes like that. So if you can remember these pieces here, again, something maybe, as you answer questions about refraction, and you have your little whiteboard, maybe you jot that down, so you remember it, but that you have to remember. Snell's law looks like that. Now remember, they won't ask you to solve Snell's law, but they will ask you about that relationship. What happens to the transmitted beam when refraction occurs? Okay, so now the test signal has interacted with the patient. We finally covered the first 3 on our list over there. Would you believe that was all of chapter 3 right there? That's it. Full chapter. 5 minutes. Full chapter. That's the difference between reviewing information and learning it for the first time. Okay, any questions about this? Does this all sound familiar, make sense? All right, so now we've interacted with the patient. Now this signal that we created is gonna come back out. That's the whole point. We've done all of this to get some sort of signal out of the body and back into the system so that we can see how it changed and create an image out of it. So the signal's been changed by the body, and it comes back out, and so now we're ready to detect the signal and process it. It's been modulated. When we say something has been modulated, it just means that it's been changed. So we sent an ultrasound wave into the body. It had a particular frequency, it had a particular amplitude, it had all that stuff with it, wavelength, all that, and what we get back out of the body is going to be different. The frequency, when we're talking about imaging, straight imaging, we're just talking about creating a 2D grayscale image, the frequency hasn't changed. That's not what changed in our case. The frequency didn't change, wavelength, all that stuff didn't change, but what changed was an amplitude, right? The higher the reflection, the more energy, the more amplitude got sent back. The lower the acoustic impedance mismatch, the less energy came back, the less amplitude came back. So it's, when we're talking about that image, we're talking about changes in amplitude. So we send into the body something that, you know, maybe looked like this. We had a pulse. That's a really long pulse for imaging, but whatever. We had a pulse. It had particular wavelength to it, had this particular amplitude and all that. And so then what came back out of the body had the same basic, let me see if I can draw it. It's the same basic frequency, but it has all these kind of weird bumps and wiggles to it. So it still has the same basic frequency, wavelength, all that, but it's not the same amplitude anymore. For one, overall it's smaller. The amplitudes overall are smaller, and it has all these kind of weird bumps and wiggles to it. So that's the whole point of those 5 receiver functions we talked about. We talked about amplification, compensation, compression, demodulation, and rejection. So the whole point of these 5 things is to get this kind of weird looking signal into something that we can assign values to and create an image out of. So all these different bumps and wiggles that are on here represent acoustic impedance mismatches. So every time there's a little mismatch, there's a little bump on our waveform. So then we have to kind of, well, we don't, but this machine goes through this process to kind of figure out what those bumps and wiggles mean. What are the acoustic impedance mismatches we're talking about? How big were they? What do I put that, how do I display that on the image? So what the whole, when we have to do the amplification process, and I think you guys have got the hang of that. Amplification is, okay, these signal that came back to the system is very, very weak. So, to keep that in perspective about how weak it is, we send out, that was that whole idea of decibels. We send out a particular power of our ultrasound beam, and then what comes back to us is not the same power. It's on the order of, I don't even remember, it's like 100 decibels different. I mean, it's this amazing difference. It's amazing to me that it's even higher than that. It's like 1/100,000th of the power that we send in is what we get back. There's a lot of attenuation that goes on in that signal. So the signal that we get back out is much weaker than what we send in, power level wise. So in order for the whole rest of the system to even be able to process that, we have to go through amplification. And so the system will do some amplification on its own, right? Amplification is just turning up the volume on all the received signals. Then we have further control over amplification in the form of gain, or what's called receiver gain. Remember, this is on the receive end. So if I turn the receiver gain up, I am not exposing the patient to any additional acoustic energy. It's just turning up the volume on what we got back. So there's some amplification that's done for us, and then there's some amplification that we can continue to do to fine tune. So we do amplification, then we can do compensation. Compensation is that increasing the echoes that came later in time, increasing the amplitude of the echoes that came later in time. And again, there's some compensation that happens in the system automatically, and then we have further control of compensation by using the TGCs, time gain compensation, that's what that stands for. So I can continue to adjust that. If you've noticed, I don't know how many of you have noticed, but when you're on some of our systems in the lab that are a little older, your TGCs look like this, right? They're kind of in a slope. If you looked at all the sliders, they kind of look like this. How about the newer, like P5 ones? What does your TGC look like when you use those? it's almost straight up and down. In fact, sometimes it looks like this. The sliders are in weird patterns. It's because the newer systems did more compensation for you, so you don't have to do so much. It's called pre-compensated TGCs. They've done a lot more of the work for you, so you don't have to do as much work. The newer systems that we just got, new to us, they're not new, but they're new to us, and even the P5s, they have an auto-optimize button that automatically tries to make your picture as pretty as it thinks it can be. So it does a lot of gain and TGCs for you, so you don't have to work so hard. The older systems we have don't do that so much. Then we do compression. Remember that the dynamic range that we have in these signals is so huge that we have to do some compression in order to make it usable by the rest of the system. And again, most of this compression is done in the system itself. We do have a compression knob. The compression knob we have is more display compression, not necessarily compression here, but we do have a compression. And then demodulation, this is the one that's the signal detection thing. And remember, demodulation is 2 steps. Rectification, smoothing or envelope detection. So in this step, this is the step that's really going to separate out what we sent in from what we got out. So we sent in this raw signal, and say we sent in something that was 2 megahertz. We know we sent in a 2 megahertz beam with that frequency, and we know what amplitude we sent in. So then what came back out was roughly 2 megahertz, but it has all these weird frequency changes in it. There's kind of this weird mixing. We talked about the mixer in relation to Doppler signal detection. There's also kind of a mixer in imaging signal detection in this demodulation step that kind of mixes this signal in with the signal that we know we sent it in and separates them out. So we kind of subtract out the 2 megahertz beam that we know we sent in, and then we get back out what's left over was this weird thing that we drew, in the PowerPoint, and we said that, okay, this is what we do the amplification, compensation, compression, all that stuff on. So to get these bumps, and these are the bumps and wiggles that are here. But to get them off of this, we subtract out what we sent in, and then we're left with this. It's the same idea, actually, as what happens with a radio. You have a radio in your car, and there's a radio signal coming from the station. They have a carrier frequency, the frequency that you turn your knob to on the radio, that's the carrier frequency. And so it's at 89.1, and it's, FM is that in I can't remember, it's megahertz, kilohertz. Anyway, so that's the frequency that the song is being transmitted on, and then your radio has a receiver, and it receives that, and it subtracts out that frequency from the song, and all you're left with is the song. Your radio is an ultrasound machine. It's a radio machine, but same idea. It's detecting a frequency and looking at the changing amplitudes. That's what it does. So we just have a big, huge radio. That's what we have. So it's the same basic idea. So we have this, we go through all these processes, we end up with this cool thing of bumps and wiggles. We go through all of these processes, amplification, compensation, compression. We've done the demodulation. Eventually we'll do rejection. Rejection is just to kind of get rid of low amplitude signals that are just basically noise, and we're left with this raw signal. Well, once we get done with all those processes, we go from that kind of weird raw thing to, mine is not going to look exactly like that, but something like that. And so remember that this, once we've gone through all the processes and we've done all the rejection and demodulation and compensation compression, we're left with something that is called A mode. A mode stands for amplitude mode. It's amplitude versus time. They will ask you what A mode stands for. Amplitude mode. It's this graph that represents the amplitude of these acoustic impedance mismatches, the amplitude versus time, and time is related to, if it came later in time, it's related to depth. Okay, so from here, once we get through the receiver functions and it does all this, now we have to get through the rest of the system. So at some point, this has to go into, we have to send this signal into an analog to digital converter. So this is an analog signal, and the rest of the system is digital. So we have to convert this analog signal into a digital signal into numbers. That analog to digital conversion can happen before the receiver, or it can happen after the receiver, depends on the system. Newer systems, the analog to digital conversion happens earlier in time, or earlier in the process. It might happen here before it goes into the receiver. Older systems, it happens after the receiver. So we go through analog to digital conversion. Once we've gone to analog to digital conversion, then that signal gets sent to the scan converter. The scan converter has two main jobs. It assigns the grayscale value to all these amplitude changes. And it organizes the lines. Okay, so really what the scan converter is a digital memory, block of digital memory with a microprocessor. It's a computer. And what that does is it converts each of the scan lines and gives them their grayscale values, organizes all those different scan lines from each pulse, puts them in the right order, gets all the values in the right place, and organizes those into an image. So once all this information leaves the scan converter, that's what gets us our image. So from the scan converter, that image can go to our display device, whatever that might be, or our storage device, whatever that might be. Remember that it goes to those independently. So what we get in storage doesn't necessarily match what's on our display if we don't have them kind of synchronized. And you just took a test over some of the stuff about the display. Remember the displays about interlace versus non-interlace? That's one of the questions I marked the Scantron wrong because I got them backwards when I was making the key between interlace and non-interlace. And how many lines per frame there are, frame rates, how many lines per frame there are on the displays. They don't ask a whole lot of questions about storage devices. The newer digital storage devices are better than our old analog storage devices, like VCR tapes and stuff like that. Remember there's that whole idea of pre-processing and post-processing. Pre-processing is anything that can affect the signal before it gets here. Pre-processing is all of this stuff that happens before we get to scan conversion. Post-processing is something that we can do to this signal once it's been stored. So post-processing typically is things like measurements, calculations. There's a few other things that we can do once it gets to this point. But pre-processing traditionally is anything leading up to the scan converter, and post-processing is anything past the scan converter. In fact, it's a little fuzzy nowadays because there's more things, because this analog to digital conversion thing happens earlier in the process. There are things that were traditionally pre-processing that now have become post-processing. So big example of that is gain. If you go to our older systems, say like the Sonos system in room 1, once you freeze the image, you can no longer change the gain. If you turn the gain knob, it doesn't do anything. On the GE systems, all of our GE systems, if you freeze the image, you can turn the gain knob and it actually still affects the image. It's because they did that analog to digital conversion here. They had more raw signal processing than the Philips machines that are older.
So it is a post-processing?
It's technically supposed to be pre-processing because gain is here in this receiver function, but newer systems have kind of taken that out. So for testing purposes, it's still pre-processing. So the rule of thumb is, if you freeze the image and you can still do it, you can still change like the compression knob, and there's a couple of things that you can still change with the image frozen, that's post-processing. If you freeze it and the knob no longer works, that's a pre-processing knob. And for the most part, that's the entire first volume of our 2-volume set. So the rest of the stuff that we have to talk about relates to some of the Doppler and hemodynamics. There's just a couple things I want to talk about. Yeah.
Are they gonna ask a question like number 53 on the text?
You have to read it to me, I
It
don't know.
was the study was performed in
Oh, yes,
Mhm.
ambient light.
ambient light.
So the idea with that ambient light thing is that if you change, say you take your machine, you go into the, like that example, you go into the OR where you can't turn the lights out. And so in order to see your image, what would you normally want to do? Because your image is going to look too dark because the light around you is too bright. So what do you want to do if your image is too dark? You typically, our first, contrast is what you should do. But typically what our response is if an image is too dark is to do what? Turn the gain up. So then when you take that image back down to our dark ultrasound room, what does it look like? It looks like crap because it's overgained. So the idea is that when you're in ambient light, what you have to adjust is the monitor, not the system. So you're going to adjust the brightness and contrast on just the monitor and leave your gain and TGCs and stuff that are going to affect the image that went to storage alone.
Is it going to be worded like that too? Because honestly, I got really confused. Just the wording of it.
I believe I took that question out of a registry review book. So I don't know if it'll be worded exactly like that, but you may find something along those lines. So let me see if there's anything. So like I said, we basically, I mean, from the time we started till now, that was pretty much everything in this first volume. There are a few topics that I probably didn't talk about. We were kind of hitting the high points here. I can't think of anything offhand that's really. One of the things I didn't really talk about a lot in here is the whole idea of decibels. The couple of things to really keep in mind when they ask decibel questions. Some of you will get decibel questions, some of you won't. Remember the shortcuts. If it's a 3 decibel change, that's a factor of 2. So if they say they change the power by 3 decibels, they cut the power in half, or they double it, depending on which way they move. And if it's a 10 decibel change, it's the same as a factor of 10. So right there. 3 decibel change equals a factor of 2 change. 10 decibel change is a factor of 10. Or if we did 20 decibels, it just keeps going up, factor of 100, and so on. 30 decibels would be 1,000, something like that. And this works for power and intensity. If they ask about amplitude or usually receiver gain, everything doubles. 6 decibels is now a factor of 2 and 20 decibels. Because we had the 2 different forms of the decibel equation, one 10 times the log of power 1 over power 2, or 20 times the log, amplitude form versus power form. But if you can remember this and this, you can pretty much answer any question they would ask you about decibels. They're not going to ask you to convert it, they're not going to ask you to do the math about it. They're going to say something to the effect of, their power's been reduced by 50%, that's a factor of 2. How many decibels has it been changed by? 3 decibels. Or they'll go the other way. There's been a 3 decibel change in your power. What factor is that? How much has the power been decreased? By half, by 50%, something like that. If they ask it related to gain, it's just double everything. 6 decibels is a factor of 2. So they turn the gain knob, they increased the gain by 50%. That was increased by 6 decibels. And some people get questions about decibels, some people don't. So I've had people come back to talk to me and I've heard both things. I've heard somebody say, I didn't have any questions about decibels at all. And other people say, man, I had a couple, it's never more than two or three. So there's not very many. You can usually guess your way through them. Don't forget your terminology, things like what it means to be anechoic, hypoechoic. When we talked about transducers, we didn't talk a lot about the bandwidth stuff. Remember that bandwidth is just that range of frequencies over which the transducer is useful. Usually don't have to go a whole lot about that. Really have to know how those transducers make their, I think what gets most people with transducers is how each transducer makes the image, you know, the sequencing and steering and phasing, all that, get down which transducer does what. There'll be application kind of questions for system operation, so similar to what I've done, here's an image, what's wrong with it, what would you fix, and that's gonna be those interactive ones. You'll be given an image and maybe the overall gain's too low, so you'll have to click the buttons to turn the gain up. The TGCs will be out of whack, so you have to slide the TGCs to fix the band that's dark. Could be Doppler related, you have to fix the color scale or the Doppler scale or Doppler gain, maybe the Doppler gain's too high and something like that. So there'll be application ones like that. How would you fix the image?
And there's free examples of that on the...
There is one example of those interactive questions on the website. You can interact with all of the different buttons, but there's only one question that it asks you, how would you fix this? But you can interact with the buttons that way. Okay. So a couple things about Doppler. There's just a couple things I want to review. Remember your Doppler equation. Now, I've been nice, and I go back and forth about being nice or not. I've been nice, and I give you the equations for the tests. They don't give you the equation necessarily on the registry exam. And I've had students come back and say, you know, you should make us memorize those equations so that when we take a registry exam, we know them. And I go back and forth with that idea about maybe I should, but I also want you to get in the habit of looking at the relationships in the equations and not just memorizing a whole bunch of useless facts. So I give you it so you can look at the relationships. Plus I figure that once you've learned it, it's much easier to go back now and look at all this stuff than it was to learn it the first time. So I know before you go take the registry exam, you're gonna spend time with this stuff and you'll look at it and go, oh yeah, I remember that now. Versus the first time you learned it when it's like, oh, so. They'll ask you relationships. Again, relationships, I cannot stress that enough. All the relationships that are here. And remember when you're looking at this Doppler equation that this is what the machine detects. This is the Doppler shifted frequency. So remember, imaging and Doppler are different. Imaging, we're detecting amplitude changes, acoustic impedance mismatch. With Doppler, we're actually looking at a frequency change. So it's a frequency and amplitude. Remember, frequency and amplitude, power disjoint, there's no relationship. So they're two entirely different ideas. The cool thing about our systems, and what still blows my mind about our systems, is it can do both things at once. It's like, it's crazy. So this is all about a frequency shift. One thing that I don't know if I've made very clear, but if you look at your systems, you'll find it, is that when our systems are doing Doppler and imaging at the same time, they're even doing them at different frequencies. The frequency that you image at is different than the frequency that you're sending a Doppler signal at. And it'll tell you on the machine what it's doing Doppler. So you picked up the 7 megahertz transducer, so you're doing a carotid, and you picked up the 7 megahertz transducer, and you're imaging at 7 megahertz. When you turn on Doppler, on your spectral display, you have the spectral display, and there's a whole bunch of numbers over here, and one of the ones that we've paid attention to is this one. There's another one up here. the Doppler frequency that it's doing Doppler at is always lower than the imaging frequency. We always do Doppler at a lower frequency because of this whole idea of sensitivity and all that. And because Rayleigh scatterers are such weak reflectors that if we did Doppler at a higher frequency, those weak reflections would be attenuated out, we wouldn't get any Doppler signal. So we always do Doppler at a lower frequency. My husband is calling me. You'll have to wait, honey. Anyway, so remember with Doppler, you're detecting the Doppler shifted frequency. You know the operating frequency. This is the one that you picked up the transducer and you told the machine. Now you know that it's not really the frequency of the transducer, but it's whatever that transducer decides to do Doppler at. But you tell the machine this, and you tell the machine this. It detects this. It assumes this, and it calculates this. So when you sit down with the machine and you turn on PW Doppler, that tells the system what operating frequency you're using, and then you turn the angle correct knob and you tell it what angle you're doing Doppler at. It assumes propagation speed in soft tissue. It assumes 1540, which again, by the way, you absolutely have to know that number backwards and forwards and forwards. And in any variation of units, I've taught you 1540 meters per second. This is worth mentioning now. Those are just two more ways of writing it in units that they do a lot. When I learned propagation velocity, I learned it this way, 1.54 millimeters per microsecond. That's how I learned it. It also converts to 154,000 centimeters per second. These two are probably the most common ways that you'll see it, meters per second and then millimeters per microsecond. The reason they use millimeters per microsecond is that this unit is more in line with the other units that we see. You know, what do we, our wavelengths tend to come out in millimeters or micrometers. Our periods and pulse repetition periods and pulse durations tend to come out more in microseconds because we use megahertz and they come out in microseconds. So this unit tends to be a little bit more in line with the other units that we see. So just to point that out. But anyway, back to Doppler. It assumes 1540. It knows what it sent in, so then a shift comes back out. Remember, we sent in 5 megahertz, but what we get out might be a little higher or a little lower. If it's a little higher, that means the motion was towards us. If I got back out 5.003 megahertz, when I sent in 5, that means motion was towards me. It was a positive Doppler shift. If I sent in 5 megahertz and got back out 4.997, that meant the motion was away from me. I had a negative Doppler shift. So it detects the shift, and then it uses all this information and actually calculates, does the math for the velocity. So that when we have our spectral scale or our spectral display, you know, and we have our waveform on there, this axis is in centimeters per second. It's in a velocity unit and not a frequency unit. You can actually change it so it's on a frequency, and you can actually see what the frequency of the Doppler shift is that you detected. 4 kilohertz, 3 kilohertz, something like that. If you're using good technique, using 5 megahertz transmit frequency, operating frequency of 5 megahertz, and use a nice 60-degree angle in a carotid, 125 centimeters per second corresponds to about a 4 kilohertz frequency shift. When I first learned, I did CW of the carotid system, and it was all in frequency shifts, not velocities. So we talk about something having a 20 kilohertz frequency shift. That meant a really, really high velocity. Really high. Tidbit you didn't really need to know, but I felt the need to share it anyway. All right, so it calculates that. So this is why this calculation thing, this is why I harp so much on the angle correct. Because if you do not do the angle correction properly and tell it which cosine value to use, your velocity calculation is crap. So that's why I'm such a huge stickler for this, and you have to be parallel to flow. If that is not correct, this whole calculation is wrong. and you get bogus velocities. So I'm not the only one that harps on angle. You will find that anybody in the vascular world is like, angle, angle. Okay. Remember that whole idea of aliasing, and aliasing is when this Doppler shift is higher than our Nyquist limit, right? And the Nyquist limit is PRF over 2. More people missed that on yesterday's test than I expected. What do you mean you don't know what the Nyquist limit is? So what the Nyquist limit says is that this Doppler shift, whatever value this is bigger than this. And so then it'll alias. If this shift is less than this, then it won't alias. So whatever that PRF is divided by 2, so if my PRF is 10 kilohertz, half of that would be 5 kilohertz. As long as this detected Doppler shift is 5 kilohertz or less, I'm not going to alias. If it's over 5 kilohertz, I'm going to alias. Okay. One of the things that they ask sometimes is reasons for no reasons why you don't get a spectral display. You know, you have a vessel up there and there's no flow. So the first thing that could be is, you know, it could be an occlusion, that there really is no flow. It could be a bad angle. This is still something that I want everybody to really, really work on, is this idea of angle, that you have to be at proper angles. One of the things that I was noticing when grading your Venus labs is that I told you when we did the Venus labs in the first place, I said, you know, with vanes, we're not measuring the velocity, so angle isn't as important. In some way, I wish I wouldn't have told you that. The downside of that is that, or the flip side of that, is that angle still matters in getting a waveform. So if I have a vessel, my vessel's going on like that, and then what I typically want to see, you know, what my typical display would be is I'm going to, you know, kind of create that 60-degree angle. I want it to look like that. If I create a 90-degree angle, what happens? No flow, because the cosine of 90 degrees is 0. So what I found people doing when they were doing their Venus exams is that it was okay. Some people didn't have an angle correct on, they just had the little sample volume. So angle correct at this point would equal 0 degrees. And out in the real world, they actually do that. It's okay. You don't actually even put an angle correct on because you're not measuring the velocity, doesn't matter. However, you still have to create a 60-degree angle between the sample volume and the vessel. If I have no angle correct on, and I just have my sample volume, but I put my thing straight up and down like this, in there, I've still just created a 0-degree angle, and I'm not going to get any signal. Bad angle, no signal. And so I had several labs where, you know, the people are even asking me, man, I couldn't even get a Venus signal. Well, it's because you did that. Or you had this vessel going that way, Doppler steered this way. What did that create? 90-degree angle. No wonder you don't have a signal. So if you have it steered that way, if your vessel is like that, steer it like this. You don't even have to have the angle on. You know, you don't have to have the angle correct on to do Venus, but put your Doppler line with the vessel instead of against the vessel. So bad angle, whether I'm angle correcting or not, if my Doppler line is at a bad angle to my vessel, I'm going to have a crappy signal or no signal. So bad angle. A very weak signal. Remember, these are Rayleigh scatterers. So our signal is weak anyway, so if I end up with an even weaker signal, I may end up with no flow detected, or this might relate to, you know, poor sensitivity of the system itself. Along that idea, If my wall filter is too high, poor system settings, so things like wall filter or gain. If my gain's too low or my wall filter's too high, I'm not gonna have any signal in there. That also happens in the lab a lot, that one of the P5s, for some reason, the wall filter always comes up really, really high. And then you're trying to find perineal artery, or you're trying to find flow in the calf veins, and you can't get any flow. It's because the wall filter was so high that it was taking out this much of your waveform. And so where does the venous flow sit? Right there, right where it was filtered out. So you have to really watch that kind of stuff. Okay, so those might be reasons. So they may ask you on the test, which of these would be a reason for no detectable flow, or no spectral Doppler waveform, or no color? Some of the same stuff, it's same for color as it is for spectral Doppler. Same thing is true for a color box. If my color box is straight up and down to a vessel like that, I'm not going to get any color in it. If my color box is this way to this kind of a vessel, not that it would be quite that simple, but if it's that way to that kind of a, with the vessel going that way, never going to get any flow out of it. So while, yeah, we don't necessarily have to angle correct, you do have to really pay attention to what angle am I creating to that vessel. Think about all the different ways. One of the other things that they ask about is all the different ways that you can create spectral broadening. So if I have a vessel along here, and typically we want a small sample volume right in the middle of flow. You know, and I'll have my angle correct up there, that's all good. If I have a small sample volume right in mid-flow, assuming I have, you know, a parabolic flow profile there's parabolic flow, I'm going to get that beautiful waveform that has a window, everything looks great. If I open my sample volume up wider, you know, maybe I'm still at a good angle, but I open my sample volume up wider, I'm detecting more of these range of these velocities in this parabolic flow profile, so that's going to create spectral broadening. If I have a small sample volume up here close to the edge of the wall, if I'm on this edge of the parabolic flow or this edge of the parabolic flow, that has more range of velocities than it does in the middle because of the shape of the parabola. So this is going to create spectral broadening. If I have a sample volume so huge that it's outside of the vessel, not only am I going to get spectral broadening, but I'm probably even going to pick up more vessel wall thump. I'll have these kind of low amplitude, or not low frequency, high amplitude thumps in my waveform, because I'm not only detecting flow inside the vessel, but I'm detecting the wall motion. That's going to increase my spectral broadening. If I'm using continuous wave, remember continuous wave listens, it doesn't have a sample volume, it listens across that entire range. So I'm definitely going to have spectral broadening when I'm using CW. And then the last reason I would have spectral broadening is if there was actually turbulence present. You know, so if I have a stenosis and I have the turbulence out here, I'm going to detect the spectral broadening here in the turbulence, but I also will likely have spectral broadening even here in the stenosis, because if you think about it, that's very, very, can I get my sample volume small enough to be in the middle of this? And usually flow inside a stenosis isn't parabolic anymore anyway, it becomes more plug. But I'm not going to be able to get a sample volume small enough to just get center flow inside a stenosis. So that's typically why we end up with spectral broadening in a stenosis as well. We have not only some disturbed flow going on and multiple velocities, but we end up with this, but we end up with this small or sample volume that we can't get small enough. Okay, you know the difference between pulse wave and continuous wave. Remember pulse wave, when we're doing pulse wave Doppler, we have range resolution, but it has aliasing. The opposite is true for CW. CW, we don't have any range resolution, but also it doesn't alias, theoretically. It will display alias. Okay, that's really it. All of these kind of reasons for no flow also are present with color. The only thing different with color is, and it works a little bit for spectral as well as scale settings, but more for color, because our scale settings and color are related more to the wall filter. So if my scale setting is too high with color, I'm gonna end up with filtering out the flow too. So whenever we're trying to detect low flow with color, we really have to turn the scale down. And conversely, if I have flow that's high, if I'm trying to detect flow in an aorta and I have my color scale down really, really low, I'm not gonna get very good color filling and it's gonna be really flashy and weird because my scale is way too low for how fast the flow is going in that aorta, so I have to turn it up. Okay. There are questions about hemodynamics, so remember all those hemodynamics equation, Poiseuille's law, Bernoulli's equation, the resistance equation, all that kind of stuff. That's still all testable things that they ask questions about in the registry exam. They do ask some about the bioeffects and safety that we just did. So they'll ask about what a mechanical index is and what a thermal index is. They'll ask questions about the sensitivity, specificity, accuracy, positive predictive value, negative predictive value. There'll be a few of those. There's not as many of those, but there'll be some of those.
Do they have you figure out numbers?
Typically not. If they do, it's very simple. Or they'll ask you, how many true negatives out of this, or any math that they ask you to do is very simple math. It's something you should be able to do in your head. But again, it's more about, we know that accuracy can be between sensitivity and specificity. So they may give you a sensitivity and specificity number and then ask you what the accuracy would be. And you're looking for the percentage in between those two. They don't ask a ton about that. They will ask about some of those common intensity artifacts. They'll ask about artifacts. We didn't really talk about artifacts, but if you know all of this stuff, you can get the hang of what artifacts are and how they work. So, if you go back through all that stuff that we talked about with artifacts, about what creates them and kind of going back to those assumptions, what assumption does the machine make and how are we kind of violating that assumption. And they may ask you how to fix it. That may be one of the fix-it questions. There's an artifact present. They ask it a lot with aliasing, which Doppler doesn't quite fit into the same category as the other imaging artifacts, but we can still fix it. They do ask very minimal questions about contrast and harmonics. So again, if you've kind of got the hang of what we talked about with harmonics, sending at a lower frequency, receiving at the higher frequency, you'll get those questions about harmonics. There's not very many questions about harmonics these days, but there's a few. And a few about contrast, just those basic ideas that we talked about increasing the acoustic impedance mismatch in blood so we can see it better. That's it. Do you guys have questions? Look at that, 3 hours, we went through both volumes.
Whatever else you want to impart, I'm just trying to figure out. Without knowing what we need to know, it's hard to.
Mm-hmm. I have had many students come back and say that every chapter in our book is covered in some way. And most people that take it, that have gone through my classes say, if you go through your book and your PowerPoints and the things that we did in class, if you've got that stuff down, you no problem. The test will be slammed up.
But not level 3 stuff?
Not level 3. That stuff is not really anything that they test on. But if you can go through the chapters and, the key points at the end of the chapters, those are great things to go back through. Go back through those key points and say, okay, do I understand this? Do I understand this? Do I understand this? And every single chapter has those. So that's a good way to kind of review back through the chapters. And anything that you're, don't spend time reviewing things that you know. Don't spend time reviewing the chart with the sound and what kind of wave sound is. Mechanical longitudinal wave. Don't spend energy on that, you know that. Only spend energy where you kind of read one of those key points and go, oh, I don't remember that, let me go read that. But if you read the key point and go, then move on. Don't waste your energy on those things that you already know. You all have to tell me how you do. Text me something. And be sure to tell me who you are. I get texts sometimes from people saying, hey, Ray, Chad, what today. Well, that's great. I don't know who you are. So, some of you I have programmed into my phone. Not very many of you guys. My second year students I have all programmed.
If we don't have your slides printed, should we print them? Cause there's no way to get, they're not like on the CD in the back of the book or anything, right? Okay.
I wouldn't necessarily say you'd have to go print them all out. I was kind of trying to think about how I could get them to you if you don't have them. You should save your PowerPoints, not just print them. Save them.
How do you, save them onto your computer?
If you need last quarter's PowerPoints, I can, you guys still have access to Angel for like another day or something like that, don't you? I can stick them in there. It's really easy for me to just plop them from last quarter's folder into this quarter's folder. So I can do that really quick. Anything else? Look at that, I have time to breathe.
Thank you.